Every AI model you have ever used was trained on a classical computer. Every chatbot answer, every generated image, every recommendation algorithm, every fraud detection system, every drug candidate that an AI helped identify, all of it ran on chips that process information as ones and zeros. The same fundamental architecture that has powered computing since the 1940s. And that architecture is starting to hit walls that more transistors and faster clock speeds can no longer simply climb over. The people building the next generation of AI know this, which is why some of the most serious money and the most serious minds in computing are betting that the way past those walls runs directly through quantum physics. The result of that bet is the field of quantum AI, and the specific hardware it is producing is something that does not yet have a widely agreed name, but that most systems that put quantum processors and classical processors together on the same platform to solve problems that neither could handle alone. This video is going to explain exactly how that works, what it can actually do today versus what is still years away, and why the honest answer to whether this is the end of classical AI is both more complicated and more interesting than either the hype or the skepticism would have you believe. To understand the problem that quantum AI is trying to solve, you first have to understand why classical AI is hitting limits that are not just engineering challenges, but mathematical ones. Modern large language models and deep learning systems work by adjusting billions of parameters across neural networks, optimizing them to minimize prediction error through a process called gradient descent. Training a large modern AI model consumes weeks of time on clusters of thousands of specialized graphics processing units, burning through electricity budgets that can run into the tens of millions of dollars for a single training run. The energy consumption of AI infrastructure has become one of the defining infrastructure stories of the mid-2020s, with data centers projected to consume a percentage of global electricity that is genuinely alarming at the rates current growth trajectories imply. And the returns from scaling these models, simply making them bigger and feeding them more data, have been showing signs of diminishing in ways that the research community has been openly discussing for the past year. Hit like right now, because the specific mathematical problem hiding inside AI training is the thing quantum computing was almost designed to attack. The core of the challenge is optimization, finding the best possible combination of billions of numerical parameters in an enormously complex landscape of possible configurations is a combinatorial problem that scales exponentially with the number of variables involved. Classical computers handle this through approximation, using gradient descent to find solutions that are good enough rather than globally optimal, because finding the true global optimum in a space this large is computationally intractable for classical hardware. This is not a bug in how AI training is currently done. It is a fundamental mathematical limitation of the classical approach, and it shows up as problems like models getting stuck in local optima, requiring enormous compute to escape, or simply never converging on the best possible configuration of their weights. Quantum computers approach optimization problems from a fundamentally different direction. Instead of evaluating possible solutions one at a time and marching downhill toward a local minimum, a quantum system can exploit superposition to explore an enormous number of possible configurations simultaneously, and use interference, the constructive and destructive interaction of quantum probability waves, to amplify the paths that lead toward better solutions and suppress the paths that lead toward worse ones. The theoretical speed-up this offers for certain types of optimization is not linear or quadratic. For the right class of problems, it is exponential, meaning that a problem which would take a classical computer the lifetime of the universe could theoretically be solved in minutes. The intuition behind why interference helps so much with optimization is worth pausing on, because it is one of those concepts that seems mysterious until it clicks. When you try to find the lowest point in a complex landscape of possible solutions on a classical computer, you have to evaluate paths one by one, always at risk of getting stuck in a local valley that is not the deepest one. A quantum system running the right algorithm sets up quantum waves that travel across all paths simultaneously. Where paths lead to bad solutions, the waves cancel each other out through destructive interference, like noise-canceling headphones, subtracting unwanted sound. Where paths lead to better solutions, the waves reinforce each other through constructive interference, becoming stronger and more probable. Measuring the system then preferentially returns the better solutions, guided by this quantum wave structure that has no equivalent in classical computing. Subscribe right now if you want to understand the specific moment this stopped being theoretical and started becoming real hardware. In October 2025, Google demonstrated something that the quantum computing field had been building toward for years. Using its Willow quantum chip and an algorithm called quantum echoes, Google showed a 13,000 times speedup over the Frontier supercomputer, which is one of the most powerful classical computers currently in operation, on a specific physics simulation task. The number is dramatic enough that it needs immediate context to be understood properly. The specific task was chosen to highlight quantum properties rather than to solve a direct commercial application. And the broader physics community noted that this should not be interpreted as a general-purpose speed-up in everyday computation. But what made the Willow result genuinely significant was the error correction performance underneath it. Google demonstrated that as the system scaled to larger logical qubit sizes, the error rate decreased rather than increased, achieving what researchers call below-threshold error correction, which is the mathematical prerequisite for building fault-tolerant quantum computers that can run reliably enough to tackle real-world problems. At around the same time, IBM was pursuing a parallel path with its Nighthawk processor, a 120-qubit system connected by 218 improved couplers, capable of running circuits up to 30% more complex than IBM's previous generation. IBM announced publicly that it is targeting verified quantum advantage by the end of 2026, and in this context, advantage means outperforming the best available classical methods on a commercially relevant problem, not one engineered to showcase quantum properties. Their roadmap extends to fault-tolerant systems by 2029, with Nighthawk scaling toward 15,000 entangling operations and over 1,000 qubits by 2028. IBM also unveiled a companion chip called Quantum Loon, specifically designed to test the hardware infrastructure needed for error correction at scale. And those milestones are arriving in a field where the research intensity has been accelerating dramatically. The number of peer-reviewed papers on quantum error correction more than tripled between 2024 and 2025 alone, and the engineering infrastructure around quantum hardware, including cryogenic control electronics, quantum error decoding systems, and hybrid classical quantum software stacks, has been maturing in parallel with the processors themselves. If you're starting to see why the title of this video says this could be the end of classical AI, go ahead and smash that subscribe button, because the next part explains the actual architecture of how hybrid chips work in practice. Here is what is actually happening inside a quantum AI hybrid system, explained in terms that do not require a physics degree. The classical and quantum processors in a hybrid system are not interchangeable. They are deeply complementary, assigned to the parts of a computational problem each one handles efficiently. The classical side, running on GPUs, CPUs, or AI accelerators like TPUs, handles data ingestion, preprocessing, large matrix operations, inference, and the overall orchestration of the workflow. This is what classical hardware is extraordinarily good at. The quantum side handles a specific set of provide a meaningful advantage, things like high-dimensional optimization, sampling from complex probability distributions, and simulating quantum mechanical systems that classical hardware cannot model accurately at scale. The way this plays out in a practical hybrid workflow is that a classical system prepares a problem, encodes the relevant portions of it into a quantum processor via a process called state preparation, runs a quantum algorithm on the quantum hardware, measures the output, and feeds those results back to the classical system to guide the next iteration of computation. This cycle repeats many times in what researchers call a variational quantum circuit, or adjusted by the classical processor between iterations to optimize the result. The resulting algorithm structure is called a variational quantum eigensolver, or VQE, when applied to finding the lowest energy states of molecular systems, and the quantum approximate optimization algorithm, or QAOA, when applied to combinatorial optimization problems like scheduling, routing, and resource allocation. The reason these hybrid approaches are the dominant paradigm right now, rather than fully quantum approaches, is that the quantum processors available today, what the field calls noisy intermediate scale quantum devices, or NISQ machines, are powerful enough to perform meaningful computations, but not yet reliable enough to run long quantum circuits without accumulating errors that destroy the result. By using the quantum processor only for the specific subroutines where quantum advantage exists, and keeping everything else on the classical side, hybrid systems extract quantum value from hardware that is not yet fault-tolerant, which is precisely the hardware that exists today. Here's a real example that has already moved out of the laboratory and into actual financial infrastructure. HSBC worked with IBM Quantum to test whether quantum machine learning could improve financial prediction models for market behavior and bond trading data. The team used quantum kernel methods, a technique that maps financial data into a high-dimensional quantum state space where classical machine learning algorithms struggle to find patterns, and compared the results against classical machine learning approaches on the same data. The quantum-assisted models reduced prediction errors and improved accuracy on certain scenarios, demonstrating that quantum AI is not just a future promise, but something that a major global bank is already testing against its real operational data. The quantum kernel approach deserves a bit more explanation because it sits at the heart of why quantum systems can outperform classical ones on specific machine learning problems. Kernel methods in machine learning work by measuring the similarity between data points in a high-dimensional space, where complex patterns that are invisible in the original data become linearly separable and much easier to classify. The challenge is that computing similarities in extremely high-dimensional spaces is computationally expensive for classical hardware because the resources required scale exponentially with the number of dimensions. A quantum system can encode data into a quantum state that naturally lives in an exponentially large Hilbert space and compute similarities using quantum interference, accessing that high-dimensional structure without the exponential classical cost. This is not a trick or a workaround. It is a genuine structural advantage that arises from the way quantum information naturally works. The drug discovery application is worth expanding on specifically because it represents the clearest near-term path to quantum AI, delivering measurable economic value in ways that affect ordinary people. Pharmaceutical companies spend billions of dollars and over a decade of time on average to bring a new drug from initial discovery to market approval. A significant fraction of that cost comes from the difficulty of predicting how drug candidate molecules will behave when they interact with biological targets, which requires simulating the quantum mechanical behavior of electrons in molecules with precision that classical computers fundamentally cannot achieve for large, complex molecules. This is not a computational limitation that faster classical hardware will eventually overcome. It is a fundamental constraint arising from the exponential scaling of the quantum mechanical equations involved. A sufficiently powerful quantum processor running a variational quantum eigensolver algorithm could simulate these molecular interactions with the precision needed to identify promising drug candidates reliably before expensive laboratory synthesis and testing, potentially compressing years of trial and error into weeks of quantum simulation time. Several major pharmaceutical companies, including Roche, Pfizer, and Boehringer Ingelheim, have been running quantum chemistry programs in collaboration with quantum hardware companies, testing whether quantum circuits can already deliver useful molecular simulation results on today's NISQ hardware, and the results from these early programs are one of the primary reasons the investment in quantum AI hardware has been accelerating rather than slowing despite the ongoing engineering challenges. Go ahead and hit that like button, because what comes next is the question the industry is still actively arguing about, which is the honest timeline for when this becomes transformative at scale. Not everyone agrees on when quantum AI hybrid systems will be capable enough to make a material difference for mainstream artificial intelligence workloads. Jensen Huang, the CEO of NVIDIA, whose graphics processing units currently underpin the vast majority of AI training infrastructure on the planet, has publicly estimated that genuinely useful fault-tolerant quantum computing is still 15 to 30 years away. His position carries significant weight not only because of NVIDIA's centrality to the current AI industry, but because he points to specific technical obstacles, primarily the enormous engineering challenge of building the error correction infrastructure that fault-tolerant systems require at scale. One of the most serious obstacles that often gets underreported in popular coverage of quantum AI is the data encoding problem. For a quantum processor to provide a speed-up on a machine learning task, it first has to load the relevant data from the classical world into a quantum state, a process that requires a piece of hardware called a quantum random access memory, or QRAM. Building a QRAM that can load large data sets fast enough to maintain a practical quantum speedup remains one of the most significant open engineering challenges in the entire field. If the time required to encode data into the quantum processor is comparable to or longer than the speedup the quantum computation provides, the hybrid system loses its advantage before the quantum processor ever starts running. This is a real constraint, not a theoretical objection, and it is one of the reasons why the near-term quantum advantages are expected to appear first in problems involving small, carefully structured data sets rather than the massive training sets that modern AI relies on. Google and IBM, on the other hand, are targeting commercially relevant quantum advantage within the next 2 to 4 years, with fault-tolerant systems by the end of this decade. IonQ, using trapped ion technology rather than superconducting qubits, demonstrated a 12% performance advantage over classical supercomputers in medical device simulation. In early 2025, a smaller but commercially focused result that points toward near-term practical applications in highly specific domains. The DARPA Quantum Benchmarking Initiative is attempting to bring independent, standardized assessment to these competing claims, because the quantum field has learned painfully from past episodes of premature announcements that clear external verification of progress claims is essential for the community's credibility. The honest position that emerges from examining all of this carefully is that the answer to when quantum AI hybrid chips become transformative depends heavily on which specific problem you are asking about. For certain optimization problems in logistics, portfolio management, and drug molecule energy simulation, quantum subroutines running inside hybrid systems are already providing measurable improvement in experimental deployments right now in 2026. For the kind of general purpose, large language model training that powers the AI products most consumers interact with daily, the hardware and algorithms needed to deliver a genuine quantum speedup do not yet exist. And the realistic timeline for when hey might is genuinely uncertain, with serious, technically credible people disagreeing by a factor of roughly 5 to 10 years. What is not uncertain is the direction of travel. McKinsey published analysis noting something important about the quantum AI relationship that tends to get lost in the excitement about quantum hardware, which is that the relationship between quantum computing and AI runs in both directions simultaneously. Quantum computing accelerates AI by providing exponential speedup on the optimization and simulation problems that classical AI struggles with. But AI also accelerates quantum computing because machine learning algorithms are being applied to the problems of quantum hardware itself, including optimizing error correction codes, modeling noise in qubit systems, and automatically calibrating the control pulses that manipulate qubits with the precision required for high-fidelity operations. These two technologies are not simply one replacing the other. They are actively improving each other in parallel, which is part of why the timeline to meaningful quantum AI capability may be shorter than a linear extrapolation from current hardware would suggest. A specific example of AI accelerating quantum hardware is worth making concrete. The control electronics that operate a quantum processor must generate extremely precise microwave pulses to manipulate qubit states and entangle them without introducing errors. Traditionally, calibrating these pulses has been an expert manual process, requiring highly specialized physicists spending days fine-tuning a single processor. Machine learning systems trained on the processor's noise characteristics and qubit response patterns are now automating this calibration, thus reducing a days-long manual process to hours of automated optimization, which directly improves qubit fidelity and enables faster iteration on hardware improvements. AI is not just a beneficiary of quantum computing. It is an active contributor to making quantum computing more capable faster. The architecture of future AI data centers is already being planned with this convergence in mind. The model that leading researchers and infrastructure companies are converging on is not a replacement of classical hardware by quantum hardware, but an augmentation where quantum processors join GPU clusters and specialized AI accelerators as co-processors, each assigned the workloads, where its architecture delivers the most value. A quantum processor handling high-dimensional optimization problems, while a GPU array handles large matrix multiplications, and a classical CPU manages data flow and orchestration, is the data center architecture that the serious technical institutions are building toward, not a world where classical computing suddenly becomes obsolete. The idea that this is the end of classical AI is therefore the wrong frame for understanding what is actually happening. Classical AI is not ending. It is developing a fundamentally new partner that can handle the specific categories of problems that have historically been the bottleneck in classical AI's ability to go further. The limitations that quantum AI is designed to address are real, and the evidence that quantum hardware can address some of them is no longer purely theoretical. But the timeline is longer than the most breathless coverage suggests. The problems solves first are more specific than general-purpose AI acceleration. And the near-term future is firmly hybrid rather than purely quantum. The more accurate frame for understanding this moment is that we are watching the early stages of computing's next major architectural transition, the kind that only happens a few times in a generation. The transition from vacuum tubes to transistors, from mainframes to personal computers, from single-core to multi-core processors, from CPUs to GPUs for AI training, each of these transitions looked gradual and uncertain from inside the moment and obvious in retrospect from outside it. In each case, the people dismissing the new architecture as impractical were making technically accurate observations about the current generation of hardware. Vacuum tube computers really were more reliable than early transistors. Early GPUs really were awkward tools for AI researchers before the software ecosystem matured around them. The critics were right about the present and wrong about the trajectory, because architectural transitions compound their improvements in ways that linear extrapolation from current limitations systematically underestimates. Quantum AI hybrid systems are the next transition in that lineage, and the degree to which you understand how they work and what they can actually do right now is the degree to which you will be prepared for the world they create rather than surprised by it. The organizations building quantum AI literacy today running experimental hybrid workflows, training teams in quantum algorithms alongside classical deep learning, and establishing partnerships with hardware providers, are building a 3 to 5 year head start in technology the broader industry will scramble to adopt when the fault-tolerant milestone arrives. The history of every major computing transition shows that this head start compounds into a structural advantage that latecomers find very difficult to close. Hit that like button, subscribe to this channel, and turn on notifications, because this field is moving faster than almost anything else in technology right now, and the next benchmark, the next hardware announcement, the next demonstration of real-world quantum AI advantage could arrive from any direction, any week. You deserve to understand it when it does.